Okay, so welcome to the Simons Institute. My name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute for the Theory of Computing. I will just make a few brief remarks before handing it over to the workshop organizers. A quick introduction to the Simons Institute. So this is the leading international venue for collaborative research in theoretical computer science. It was established in 2012 with a generous grant from the Simons Foundation. And every semester, the foundation, the institute brings together the world's leading researchers in the theory of computing and related fields, as well as the next generation of outstanding young scholars. And we typically run 2 programs each semester, each bringing together about 70 researchers, junior and senior. And each of these includes a boot camp and a few workshops, typically 3 workshops that bring more visitors here. And I would like you to welcome you to the workshop on structure of constraints in sequential decision making, which is the 3rd of 4 workshops in the semester's program on data-driven decision processes. Last week, there was a joint workshop, which was an extra workshop in this program. And I would really like to thank the organizers for their hard work in putting together an exciting program this week. And they are Shipra Agarwal and Balu Sivan, and they will give more pertinent remarks about the workshop shortly. So, thanks again. And a quick logistics about the coming week. Food is provided before the first talk outside and also during the breaks. And for lunch, you are on your own, but there are many excellent options in the vicinity. And we ask that you please leave food and coffee and such outside the auditorium. It helps us keep the auditorium clean. Water in bottles is fine. And if you want to leave your stuff while going out for lunch, there are lockers on the other side, on the other side, and you can lock your bags. And our videographer, Omed Far, will help speakers set up for talks in case you have any issues. And finally, I would like to give a special thanks for our events team, Kelani, Ashley, and Elizabeth, for managing all the logistics for this week's workshop, including accommodations for all the out-of-town visitors. So with this, I'll hand over things to the organizers. I believe Shipra will say a few words about it. Thanks and have a great week. Yes, it's Balu.
Thank you and welcome everyone. Good morning. So just a few words about this workshop. So this is the 3rd workshop, as DV mentioned, on structure of constraints and sequential decision making. We have one more workshop on societal considerations. So I'll just have a word about that workshop before talking about this, which is that workshop is soliciting posters. So the deadline is this Friday. So if you're interested, or students or others who might be interested, please pass this message. Okay, so we have 16 exciting talks for this workshop. We went with 1 hour long talks. So hopefully, we don't just get the statement of the results from the talks, but some proof techniques and some nice interactions. That's the goal. So the 16 talks will go as 4 talks on Monday and Tuesday, 3 talks on Wednesday and Thursday, and 2 talks on Friday. We'll end early on Friday, half a day. Mondays and Tuesdays will be 9:30 to 10:30, 11 to 12, half an hour break, and then 2 hour lunch break, 2 to 3, and 3:30 to 4:30. Wednesday, we'll have only 3 talks. That's because after the 2 to 3 p.m. session, we'll have a poster session. And similarly, Thursday, we'll only have 3 talks. That's because after the 3 p.m. session, there'll be an open problem session. So please do prepare some open problems and add it to the doc, which I've sent. And Friday, we'll end half a day, 2 talks. And today, after the 4:30, that is after the 4 talks, the final talk ends at 4:30, there'll be a reception, Peter Bartlett recognition event. So we'll all head over to that after this talk. I think that's it.
Yeah. Just for open problems, I just want to emphasize, if you just want to shoot us an email, that's also fine, or better add into the doc, or catch us in one of the breaks and mention your ideas. That's also fine.
Yeah, any format is fine. Like we expect to give at least 10 minutes for each of the problems, so there is hopefully some discussion, not just the statement of the problem, but some discussion. Yeah, any format is fine. Okay, good. I guess we can begin. The first topic will be by Freund on constant regret and exchange of action models. Thanks.
Thank you. The talk is about constant regret in exchangeable action models. And this is a class of problems, a class of settings that I've been thinking about for a few years now with some fantastic collaborators. The main focus of the talk today will be on work with Kamessi and Sid. In fact, if some of you went to Sid's talk on Friday, at least some of the ideas you will see today might seem at least somewhat familiar. Now, I want to do the following in today's talk. I want to start by defining exchangeable action models or the exchangeable MDPs as a class of problems and sort of make clear what sort of things we would include in that and what would not count as an exchangeable action model. Then I will try to characterize sets of assumptions where we can achieve uniform loss guarantees, where we can achieve constant regret that will not scale with the time horizon of our problem set. And in particular, that will relate both to the types of objectives that we're facing, the types of constraints that we're facing, the types of information structures that we're facing. And then I will try to give some algorithmic and analytic ideas of how an algorithm actually achieves such constant regret and how one can prove such constant regrets. And finally, hopefully I will have time to then point to some actual applications of this to problems that we might be interested in where we can then get new guarantees. As I said, I want to start by defining exchangeable action MDPs. So the setting that I'm considering is one where we have exogenous arrivals over a time horizon of length t. So we have theta1, theta2, up to theta t. And we have a constant number of possible arrivals. In each period, we observe the arrival and we take an irrevocable action. I should highlight, whenever you see the lightning, that's an indicator for danger. That means I'm treating something as a constant. And how constant this is depends on the particular lightning, but they're all going to look the same. But you should treat this as, okay, when he says constant regret, he does not care about the size of K. He does not care about the size of L. For L, it's probably often innocent. The actions might be accept, reject. That's innocent. That's just 2. For K, it might be larger. So we have our exogenous arrivals. In each period, we observe one and we take an irrevocable action. And we will denote by x theta j the number of times over our t periods that there's an arrival of type theta and we take action j. And now what I would want for an exchangeable action model is that the objective can be written as a function f of x, which I either want to maximize or minimize for some known function f. So I know the function f. I don't know the arrivals. And I want my objective to only be a function of how often did I take each action. Some of you might think, why would it only be a function of that? Basically, the sort of problem I'm excluding is one where there's a time dependency, where it makes a difference whether I take a particular action in period 3 or in period 24. I'm assuming it does not. If a particular type arrives and you take a particular action in response to that type, it's the same regardless of when that occurs. Now, I'll make some assumptions on F. I'll also make some assumptions on the arrivals. But I first want to sort of highlight the problems that would be captured in here. The first that I'm interested in is online stochastic bin packing. So we have bins of a given size. For example, let's assume our bins have size 10. And our items, our arrivals are items of different sizes. For example, the sizes could be 1, 3, 4, 5, and 8. And in each period, we observe some item, and we need to either place it into one of the existing bins, or we need to create a new bin and put it into the new bin. We can think of the bins as sort of being configurations of bins. So for example, 118 would be a configuration. It means that is a bin where we want 2 items of size 1 and 1 item of size 8. 145, 1 item of size 1, 1 of size 4, 1 of size 5, and so forth. If we denote by b theta j, this greater equal to 1, I think should actually be a greater equal to 0, now that I think about it. The number of items of a particular size that fits into a configuration. So B555, the configuration with 2 5s in it can hold 2 items of size 5. If we then denote by x theta j, the number of times that we take the action a theta j, then the total number of bins that we are going to be using can be written as f of x being equal to the sum over all different configurations, the maximum over all types of x theta j divided by b theta j, take the ceiling of that.
So
Yes.
like this is equivalent of the concepts like bin pack, where I don't have types because you assume that it's constant number.
Say again?
Like you assume that you have special types to bins, right? But you are saying that because I have constant number of types, it doesn't matter, not constant.
Yes. But actually, can you repeat? Can you
So
say?
like in normal bin packing, as I know it, I don't have fixed type for bins. They can change types as long as you go.
Yes.
Here
Yes.
you fix the types of the bins.
Yes. So I fixed the types of the bins, and I'm also fixing the sizes. But yeah, other than that, it's normal bin pack. For those of you for whom the ceiling is unnatural, not so important. All that really matters is our objective here is a function of x and only of x. It's not a function of when you take a particular action. It's only a function of how often did you take each action. Now, different example, network revenue management. We have some resources and our arrivals come with a value and a resource requirement. So our values are scalars, our resource requirements are in the same dimension as our resources that we have available. And in each period, we observe a type and need to either accept or reject. And we want to maximize the accepted values without violating resource constraints. Because I later want for my objective function to actually be continuous, rather than setting a hard constraint on not violating the resource constraints, what I will do is I will penalize any violation of the resource constraints. And other than that, I'm just maximizing the value that I achieve from all the types that I've accepted. Notice in particular, we again have an objective that's only a function of x. It's not a function of how we got to that, when we accepted or rejected a particular type. Similar, you can think of models of job assignments. There's a choice between M servers for each arrival. Each arrival is a job that needs to be processed. And the decision is which server do we want to process it at. Denote by x theta j the number of times that you send a type theta job to a type j server. And let's say our objective is the cost to process all jobs, where each server has both, for each job, a fixed cost, c theta j, and a minimum average cost per job, mj. And you will get something like this here. This is a bit unusual for a job assignment model. This was actually the original, sort of the first problem in this class that I was thinking about in a particular online platform application. In refugee placement, which is an area of study that's sort of become a neat application of optimization in recent years, you have refugee centers, placement centers, where refugees sort of first arrive in a host country. And refugee resettlement agencies need to make a decision of where should a refugee be sent when they arrive to a host country. So the arrivals are now cases of refugees. The metric of interest is the probability or the expected number of refugees that will find employment in the host country. So this is our probability v theta j for employment. This comes from some machine learning model that is already given. And then in each period, we observe a case. We need to take an irrevocable action of telling a refugee, this is the center that you've been assigned to. And by x theta j, we would denote the number of times that a case with a particular employment vector probability is assigned to a particular location. And our objective would again be to maximize the employment, where we are penalizing resource capacity violations in the same way as before, meaning each of the centers has a capacity and we don't want to send more people to that center than we have capacity for.
in this case, what is
theta would be, so if you think about the machine learning model, it predicts the employment of the arrival for, so a person comes in, the machine learning model tells me you have a probability of 0.8 of finding employment here and probability of 0.2 of finding employment there. And that would characterize the type.
So it's like their preference, and in some sense,
we can think of it as preference, but preference is actually not what matters. What matters is sort of the probability of finding employment. Okay. This is work that
prediction for each.
Yes. So for each one, based on a number of covariates that these resettlement agencies have access to, there is a prediction of their ability to find employment in different locations.
Theta is like a vector.
Yes, you can think of it as a vector where each location j is indexed by is given by v theta j. Now there are a lot of things clearly that are captured here. It's worth highlighting things that are not captured. So one thing that's not captured in particular is any sort of bandit setting. So if I have an arrival in a bandit setting, I pull an arm and I don't know what the outcome will be. That's sort of the whole point of the explore-exploit aspect of it. Here I assume that f is known. So whenever the objective is unknown, that's going to be a bit tricky. Yes.
So is this basically the full information setting where before placement you have this type theta, and that's all the information that you need in hindsight to make the optimal decision? So this f function depends on the sequence of the whole thetas, and then you made the assumption that it depends on the actions in such a way that it depends on the actions through their frequencies only. That's it.
Yes.
That's the full information setting with this concept.
Yes, and you don't necessarily know the arrivals beforehand, and that's where the good complication comes
that's
from.
When online learning is going to come.
But in terms of like, if you knew the arrivals, the problem would be trivial. Yes. Another thing that's not captured is exactly when our actions are time sensitive. So Raina, I believe, will be talking after this talk about a setting where we do bin packing, but the size of the job sort of varies across time. And that's definitely not captured, because without having seen her exact talk, I'm pretty sure in that setting, the timing of actions becomes important. So our objective depends not just on the number of times we take each action, but also on when we take them. There's another thing that's not quite captured, at least as stated now, which is the overbooking setting, which is weird because I used overbooking in the title of the talk, so I better be able to capture it. So in overbooking, I claim that I don't quite know the function f. Let me explain why. The traditional overbooking model for resource allocation would look something like this. We have arrivals that give us some value if they're accepted, but they also have some probability to be no-shows. And no-shows are great because if we accept them, they will pay, but they won't actually consume any resources. They won't show up. Think of this as being the reason why airlines might overbook a flight. In particular, this would incentivize us to admit more arrivals than we have resources for, because I get more money and I don't actually need to have more seats available because those people don't show up anyway. Now, the problem is if I accept too many people so that even the people who do show up consume more resources than I have available, then I'll need to pay a penalty for each person that I've overbooked. Now, when I admit a type, I don't know whether they will show up. So if you think about it, I have all these arrivals. There's a particular arrival of a particular type. At time 7, at period 7, I have an arrival of a particular type, and I accepted them. And that one actually ends up showing up. 3 periods later, there's another arrival of the same type. That one is a no-show. Eventually, I'll never find out because I rejected them. If I'd done it the other way around, my objective would have been different because the person would have been a no-show. So in a way, I don't know F exactly because F depends not only on the actions I take, but also on the realization of the no-showness, which I don't know. Now, if I knew all of the arrivals, should I be accepting? By arrivals, I mean their type. I don't mean their realization. If I knew the realizations, it's sort of a silly problem. Just accept all the people who don't show up, get the money without them ever showing up. It's great. Now, I claim this here should be the expression that I'd want to accept. The maximum value that I get from accepting people minus the penalty in expectation of who will or won't show up. And if I pretend that this is my objective, then it actually becomes an exchangeable action model. Now, that's not the real objective. That's just the expected objective in a sense. But if I use this as my objective, I can then compare myself with a clairvoyant, for example, which is what we'll end up doing, with a clairvoyant who knows all of the arrivals, but doesn't know the realizations. So in that sense, even though overbooking a priori might not be viewed as an exchangeable action model, once you take this view of the world, which still gives you an upper bound on the best possible policy, you get an exchangeable action model. Now, this was a quick overview of a number of different models that would fit into the setting of exchangeable actions. From now onwards, for the most part, I will actually steer away from any particular example, and I will try to make everything that I say relate to all of these examples. The benchmark that I'll be interested in throughout is that of a clairvoyant optimum, meaning the optimal solution that you would get from your actions if you knew all of the arrivals beforehand. So what am I optimizing here? I'm saying opt is equal to the maximum f of x, subject to for every arrival type, if you look at all the actions that you take, you want to be equal to n theta of t. N theta of t is the number of arrivals of type theta over the entire time horizon. And of course, I'm not allowing any action to be taken negatively. So that will be my benchmark. This is basically what you would get if you were solving the problem offline with all the information beforehand. And what I would like for my algorithm's objective to be like is I would like the gap between this optimum, this clairvoyant optimum, and my algorithm to be bounded by a constant. And of course, there's a lightning there because I'm okay with this constant depending on any lightning that you've seen before in any way. I just don't want it to depend on t, t being the time horizon. One thing that's worth mentioning is that for all the problems I've described so far, it turns out that it's sort of trivial to get square root t loss with the assumptions that we will be making. So getting square root t is really not of interest. Getting it to O of 1 is hopefully where we'll see some interesting things happening. Now, in order to make some assumptions, I want to be clear. I sort of have a family of assumptions. I have sets of assumptions, and you can pick and choose. And depending on how you pick and choose, I might be able to say, no, it's impossible to get constant loss. Or I might be able to say, yes, you can get constant loss that way.
Just to clarify in the previous, when you're denoting the algorithm's performance, why does it depend on theta 1 to theta t and not just on the number of each frequency of each theta?
In part because the algorithm's actions might depend on what the algorithm has seen so far. So if you think of an algorithm that doesn't know a priori the probability of each arrival, that algorithm would actually have to learn initially what the probabilities are, and the actions might be different depending on the arrival sequence. Whereas the optimum should also actually be a function of the optimum, I guess, should be a function of the counts.
This algorithm cannot use anything else, or you're saying that it doesn't help to use anything else than theta?
The algorithm cannot use anything else. Yeah. So possible assumptions on T. There are two settings I can allow with respect to the time horizon. One is easy and pretty standard. I know the time horizon a priori. The other is a new one that we've come up with that I actually think is a very natural one that people might want to consider more in other settings as well. T is a priori unknown, but sometime before the end of the time horizon, we get a warning. We're told the time horizon is going to end. So I don't know anything about the time horizon a priori. I don't know how it's distributed. It can effectively be chosen adversarially. But when the end is coming up, I'm sort of given a signal. Now, notice, I don't need the signal to be super far before the end. I'm putting in t to the 3/4 here. It could actually be as small as t to the 1/2 plus epsilon for some epsilon greater 0. But that would force me to carry the epsilon for a lot of the talk, which I don't want to do. So instead, I'm just going to plug in epsilon equal to 1/4. So I'm basically allowing for an adversarial end to the time horizon as long as I get a warning sometime before then. When might this be applicable? Imagine there's an open-ended marketing campaign that we started at the beginning of this semester, which was in mid-August. And now today we're told by our manager, actually on Friday, the marketing campaign will end. So rather than being told, turn it off right now, we're told at the end of the week, it's going to be over. That doesn't strike me as unnatural. If that was the case, in reality, what we would be getting is sort of a heads up of this flavor. A more natural, maybe to a computer science audience version of this would be our arrivals come in batches. And we don't know how many batches there will be. But what we do know is that our batches are all fairly large. And when the last batch arrives, we are told this is the last batch. So either one of these would basically fall into this assumption. It's sort of an assumption that I find when we first came up with it, maybe it seemed sort of unnatural. At this point, I'm sort of convinced that this is actually the natural one, and either adversarial or a priori known is less natural. So after 2 years, I've very much gotten used to this being what the real world looks like. I realize most of the audience will probably disagree with me for another 2 years. Maybe in 2 years, you will see it similarly. Possible assumptions on arrivals. Notice I can accommodate a whole range. Sort of depends on which one you want. One would be our arrivals are IID. Each type has a probability p theta that needs to be bounded below by a constant. There's my lightning. It might be independent with known sort of probabilities in each period. It might be IID with known p theta. This is strictly weaker than this one, and we can get computationally a bit better results if we do this. We can also handle having just a single sample of t arrivals as long as we know that it's drawn from a distribution and the distribution has certain properties. I don't think I'll actually go into the details on this one, but think of A1 as maybe being the one I will focus on the most, which might also be sort of the most standard one. Now, most importantly, assumptions on F. I will make 4 assumptions on F. And the first one is genuinely innocent. I need my function F to be Lipschitz continuous. Sort of makes sense if I take a single wrong action, that should not curse me. Like that should not be like the end of achieving what I'd like to achieve. The second one looks a bit weird, but it's actually not that weird. What it's basically saying is give me two different vectors of arrivals and take an optimal solution under one of the arrival vectors. I want it to be the case that under the other arrival vectors, there exists an optimal solution that is not too far away. That sounds weird, but when f, for example, can be written as an LP, then it's actually always fulfilled by some linear perturbation results from the 80s. For overbooking, it's actually much harder to show this, because for overbooking, we have a concave objective from this expectation that is nonlinear, and we only have such a result for concave objectives that have strong curvature. And the overbooking objective doesn't have strong curvature. So there we had to develop a whole lot of machinery. I'll talk a little bit about that in a bit. But the point is, this looks surprising, but it's actually not that crazy. It actually holds in a lot of settings. The last two are a bit more odd. One is, if we have an open-ended marketing campaign, in order to have the ability of getting any sort of decent result, I need my function to be homogeneous. If I have an open-ended time horizon, I don't know when it's going to end, and I want to achieve constant regret, I need it to be the case that my objective function will be homogeneous in the time horizon. Another one is, and this one is actually the one I'm sort of least happy with, because this is the one that I don't actually provably know that it's necessary. We need the existence of either a unique optimum or we need the objectives to be concave. This doesn't hold in all settings that we consider, but in some of them it does. And informally speaking, our results can be summarized as follows. If you take the right combination of the assumptions that I just gave you, you can get constant loss. If you drop one of them, then you cannot get constant loss. Now, what are the right combinations?
Just a clarifying example. So in the F, you incorporate the constraints as well in F, or?
I do so, but in a way that keeps it Lipschitz continuous. So basically, I want to penalize violations rather than actually setting it to infinity. That in some cases, when I know the time horizon, I can always avoid violating the constraints. In the examples I'm thinking about, at least, when I don't know the time horizon, I would get an impossibility otherwise. Like when I don't know the time horizon, it's necessary to do the penalization stuff. All right, so we want to get to the uniform loss, and we're starting over here. For any results that I'm showing, I will need exchangeable I actions. I will need the Lipschitz continuity. I will need the stability of the optimal solution assumption. But now there are different paths of getting there. When I know the horizon, I know the arrival sequence, not the arrival sequence, but the distribution and its IID. Then by doing some resolving log t times, I can get to uniform loss. When it's known and independent, I need to resolve some more often, but I still get my uniform loss. When it's unknown IID, I need to do the resolving step a lot more often, but I can still get to uniform loss. When the horizon is unknown, I need the homogeneity for sure. I can handle unknown IID. I need to add the concave assumption, which I don't love because I haven't yet figured out how to get rid of it. And I need to resolve t times. Or if it's known IID, sort of I'm basically back in the setting up here, and it's pretty easy to get log t. Yeah.
Resolve means you do a fluid approximation or something?
You'll see in a second, but yes. Now, few things to highlight in terms of assumptions that we're making. Let me highlight sort of why is this weird stability assumption necessary. Suppose in each period, we observe an arrival of type either 1 or 2, and we need to accept or reject them. And we're told, and it's true, the probability in each period is 1/2 independently. So we have IID arrivals of type 1 or 2, and we want to maximize over a known horizon of length t the maximum of x1 and x2 that we accept, subject to a budget of accepting at most t/2 arrivals. This is an incredibly stupid problem. Let me highlight that first of all. Like, it's a very silly problem. Basically, what I'm saying is the two types are exactly equal a priori, in the sense of in each period, probability is independently 1/2 for either one to show up. You're allowed to accept in total t/2 of them, and your objective is to maximize the maximum that you accept of either type. Now, what's nice about this problem is it sort of shows us why we need the stability assumption. Because if I have more arrivals of type 1 than of type 2, then the optimal solution will be to only accept type 1 arrivals. And it will get, basically by setting x1 equal to t/2, it will get an objective of t/2. If I have more arrivals of type 2, it's the same story. This fulfills all of the things that we want to fulfill. It's Lipschitz, it has exchangeable actions, it's IID. The only thing that's missing is O2. And the clairvoyant is always guaranteed t/2. But basically, the best thing any algorithm can do is commit to either type 1 or type 2, always accept them. And with probability basically 1/2, you will lose square root t in expectation. So this is an example that shows the stability assumption. It looks like a weird assumption. It's actually necessary to get O(1) loss. If you're going to drop it, you won't in general be able to get the kind of guarantees that we want. There are alternatives to it, in particular for overbooking. So in the overbooking setting, where we wanted to maximize this quantity here, I don't actually know how the optimal solution changes when I perturb my arrivals. There are weird things you can imagine that could happen where you accept one more of one type, and then you accept 4 less of another, and then you accept 8 more of yet another. It's sort of weird to wrap one's head around it. But what one can do is one can restrict oneself to a particular set of solutions. In particular, what we call index solutions that order by the value of a type divided by the probability of being a no-show. If you've seen the greedy heuristic for one-dimensional knapsack, where you basically order by density of value per size, that's sort of the in expectation equivalent version. And then we would accept lower index types first. In general, that's not optimal. So these numerical results here sort of show, for a particular example, the loss that you can get from that. Or not the loss, but sort of show you what the optimal solution would do versus what the index solution would do. But what we can show is that it only costs you a constant. And once you've restricted yourself to these index solutions, you can basically prove this assumption for the restricted set of index solutions. So the optimal solution might move by a lot, I don't know. But the optimal index solution will not move by a lot under a perturbation of the arrivals. And given that I can also bound the loss of only considering index solutions, I can basically decompose my loss over the entire time horizon by first saying, let's restrict ourselves to only index solutions. Let's take the hit of O(1), and thereafter our assumption holds. So you do need something here. It doesn't have to be exactly the version that we plugged in, but you'll need something that sort of keeps the optimal solution stable. Now, before I get to actual algorithms and results and proofs, I want to show some numerical results to convince you that these algorithms are actually reasonable algorithms. So here I'm showing you a sort of very silly bin packing instance with just two types, 2 and 3. The bin sizes are of size 9. With probability 3/4 we observe 2, 1/4 we observe 3. The green line is our algorithm. The red line you can think of as what's often viewed as the state of the art, the sum of squares algorithm. As you can see, sum of squares on a log-log plot goes up. Ours stays constant. Here's a slightly more complicated instance that is looked at also in a recent work, or recently published, not so recent that it was first discovered, by Gupta and Radovanovic, where you observe we stay constant. They also compare to sum of squares. And on this particular instance, their algorithm does worse than sum of squares. And sum of squares, again, is growing, whereas we stay constant. So for bin packing, we get results that beat the state of the art. Admittedly, our constants are problem dependent, and existing results don't have this problem dependence. That should be a clear disclaimer. Here's sort of a much less well-behaved problem that comes from this job assignment setting that I mentioned earlier. I don't want to go into too much detail. What I want to highlight is in this problem here, we looked at real data from credit card transactions that is not well behaved. So like this data that comes from here is, there's not a constant number of types. So like we don't necessarily know here that this would behave well. We also observe something very weird, which is like it's first increasing, then decreasing, which can happen on real data. High level takeaway is we do still get constant performance. And here we observe in overbooking, this is relative loss rather than absolute loss, that we do scale linearly, meaning our loss scales as 1/t relative to the total objective, which is equivalent in relative loss. In absolute loss, there's constant loss. Okay, so these algorithms seem to work. Let's see how they work and why they work. Now, we want to match against this clairvoyant that knows all the arrivals a priori. For analysis purposes, it's actually useful to define what I call a semi-clairvoyant that follows the algorithm up to a certain period, meaning after 10 periods, I've made some decisions, and the clairvoyant, the semi-clairvoyant, is forced to also adapt all of these decisions. But then from then onwards, the clairvoyant does what is optimal from then onwards. So notice in this constraint here, I'm basically forcing the semi-clairvoyant to follow the actions that the algorithm has taken. And I want to sort of compare this with what my fluid approximation, as Elon predicted, would be doing, which solves a deterministic problem in which the remaining arrivals are replaced by their expectation, or a proxy for their expectation. For right now, let's assume that we are in the case where arrivals are IID and known, like the distribution is known. We'll get away from that in a little bit. So in this case, I would want to, if I solve a deterministic problem, I would want to sort of solve the same maximization, but rather than having the true arrivals, I know my arrivals up until now, plus the expected arrivals in the future. I need to write t minus t a lot, and I'll just write t bar for that. Now, what I can do with this is I can create a lower confidence bound, I claim, on the number of times that an action is played by the semi-clairvoyant for the following reason. I know with high probability, and I'm not mentioning all the constants that should go in here. So like from now onwards, basically whenever there's a 1, imagine that there's a 1 with a bunch of constants attached to it. I know with high probability that for all of my different types, the number of arrivals that occur in reality over the remaining horizon is somewhat close up to whatever fluctuation there is to the expected number of arrivals. And I also know, and this is my weird stability of optimum assumption, that there's an optimal solution that the clairvoyant might pick that is at least, as for each action, would look like the deterministic one, minus some parameter delta that comes from the assumption, multiplied by how far my types are away from what they really are. Now, I don't know how far they are away, but I know they are at most square root t bar times log t bar away. So I know for every action, there exists a semi-clairvoyant solution that uses it at least as often as my deterministic solution would do, minus this error that comes from, well, I don't know the exact arrivals, so I need to incur some loss for having some error in the prediction versus the real number of arrivals. One way to think about this is, there's some solution that is the clairvoyant, and there's some solution that is this deterministic problem that I'm solving. Those two are different because they have different parameters as inputs. But coming from this solution, I can create a lower confidence bound. And with high probability, this lower confidence bound will be below the real number here. Now,
You're considering lower confidence bound on the optimal solution?
so I don't know the optimal solution, but with high probability, following this argument here, with high probability, if I subtract from my deterministic problem, basically for each action delta times square root t bar log t bar, then with high probability there exists a semi-clairvoyant solution where each action would be above the lower confidence bound. By the way, for some actions, this may very well, the lower confidence bound might be at 0. In that case, it's not a very useful one. The lower confidence bound is basically a lower confidence bound on how often an optimal solution takes this action in response to this type over the remaining horizon.
Does this assume some kind of redundancy?
And it really only assumes the stability. It really assumes.
You plug in different data, and then the solution just differs by that much. That's
Yeah.
That's it. We're just
Oh,
using
okay,
that.
that's okay. That stability is.
Yeah.
Okay.
So to be clear, this assumption, on the one hand, it carries a lot of weight here. On the other hand, bilinear programming perturbation results for a lot of natural problems, it will always hold. Now, here's sort of a not super complicated lemma now. Suppose this lower confidence bound that I've just constructed for every action and every type. Suppose those all hold true, given the current period. And now some periods transpire, time goes by, and over those periods, I observe arrivals, I take actions. And now sometime in the future, I look at, well, how often have I taken each action? Let's assume that sometime in the future, for each action, I'm still under the lower confidence bound. Then I claim that the semi-clairvoyant, at that point in the future, that is now forced to follow my actions up to that point, is still able to achieve the same objective that the semi-clairvoyant was able to when I constructed the lower confidence bounds. Why is that true? Because the semi-clairvoyant wants to get up here for this action. I've already gone up here. It's still possible to get up there. Wants to get up here for this action. I've already gone up here. It's still possible to get there. So as long as I don't violate my lower confidence bounds, and as long as my lower confidence bounds actually hold true, I'm guaranteed that the objective that was previously achievable by the semi-clairvoyant will still be achievable. That allows me to basically prove my loss guarantee. I'm going to write my loss as follows. I take the expectation of the loss, and I'll say, well, in a sense, this is the optimal solution is the semi-clairvoyant at the beginning of the horizon, which is unrestricted by any decisions that I've made already. And the algorithm's performance is the semi-clairvoyant at the end of the horizon, which is restricted by all of the decisions that I've made. I can basically use a telescoping sum to decompose this difference based on all of the periods in which I've created new lower confidence bounds and say, well, look at the difference between what the semi-clairvoyant was able to achieve at the beginning and at the end of these periods. Well, in those periods, if my lower confidence bounds were correct, I did not incur any loss at all. If my lower confidence bounds were wrong, the worst thing that could happen is that I incurred a loss of L in every single one of the periods. But then the probability of the lower confidence bounds being wrong is something like 1 over the remaining number of periods cubed. So if we multiply these here, we get something like 1 over the remaining number of periods squared at worst. So this whole thing will sum up to a constant. Now, this assumed known IID distributions. This assumed known time horizon. We'll actually see that the changes needed to get the other results are not that significant. So this main idea will still hold true. This main idea you've also seen by Sid on Friday if you came to his talk. Presented admittedly in a very different framework and mindset, but I would say it's the same main idea. So that's our first path to uniform loss. The only thing that I've not shown is that we only need to solve log t times. After each resolving, basically I claim that for each type, let me argue differently. In order to claim the log t times, I need to show that after I've resolved with some given number of periods left, a sublinear number of periods needs to be left before I resolve again. Now, you can think of this as being about a budget of actions. So how many actions can I take for a given type before I next observe an arrival for which I would be violating the lower confidence bound? And it turns out that it's sort of not too hard to see that that would be sublinear in the current number of periods left. I'm realizing that I am running out of time, so let me try to go a bit faster. Second setting, unknown horizon, known IID distribution. In a sense, there's a natural stochastic policy one would be using if one doesn't know the time horizon, which is look at the objective and look at the clairvoyant and just replace it by the expectation. You don't know this expectation, but because you don't know t, but you know p theta. And that basically allows you to still solve for this stochastic policy. Here I'm using implicitly that f is homogeneous. And I can then say, in a similar sense to where I said before, that there's a lower confidence bound on the optimal solution, on the optimal clairvoyant solution, there's an upper confidence bound on how often my stochastic policy will take each action. Skipping over a lot of math here, as long as my upper confidence bound on the stochastic policy taking each action is below my lower confidence bound of the clairvoyant taking each action, I'm guaranteed that I don't incur any loss. And basically what I then use is, as long as I learn about the end of the time horizon sufficiently early, I can always guarantee that at the time at which I learn about the end of the time horizon, I've not taken any action too early. I've not taken any action too much. So that gives us the unknown time horizon, or a priori unknown time horizon. Again, still assuming known IID arrivals. Now, what changes if our arrivals are IID, but the distribution is not known? In that case, it gets very tricky to create lower confidence bounds for the optimal solution because I don't know p theta. I also maybe don't know t. So I know neither of these parameters. One good thing is that at least initially I can compare to the stochastic policy, because I've just seen that the stochastic policy, at least at the beginning, won't incur any loss relative to the semi-clairvoyant. Now, one natural thing to do is in period t, just solve this deterministic problem, assuming that the arrivals follow the empirical distribution so far. Now, the empirical distribution so far after t periods will be close in the same sense to before to the real distribution. And that means that the optimal solution to this one here and the optimal solution to this one here are actually also somewhat close. So if we condition on this as being a good event, then we would like to just follow this solution here and be fine. But that doesn't actually quite work. And the reason is that if we solve this one here and we get something that's small, think 1 over square root of t. That one might actually be equal to 0 according to the true stochastic policy. This event holds true, but this one here is still greater 0, where this one here would be equal to 0. And because of that, we need to do some thresholding to avoid taking such an action here. And basically, there's a little bit of technical detail needed to show that in doing the thresholding, we sort of need to scale other actions up. And we need to make sure that this scaling other actions up will not lead to us actually violating the lower confidence bound of the clairvoyant for these other actions. I won't go into the necessity of like why you need to know sufficiently early before the end, but similar to the assumption O2, you also need such an assumption. It doesn't have to be this exact one. This is one assumption that can be plugged in. Also, our lower bounds on the probabilities. If you allow arbitrarily small probabilities, it becomes impossible to obtain the uniform loss guarantees. And in the interest of time, let me actually summarize with sort of the results that we've gotten from this framework for specific problems. First, for overbooking, there had been some results that had looked at sort of overbooking, including in cases where there is network of revenue management rather than just a single resource, all of which got at best square root t loss. And there'd been some results, including earlier work by Alessandro Alotto and Itai Govic and Sid and Alberto Vera, that got constant loss in network revenue management without overbooking. So the overbooking results that I basically flashed at would extend in this direction. So they get O of 1 for a setting with overbooking, though without the network. And that's based on work with Kamessi, who's in the audience. For bin packing, this table I stole from Liu and Li from last year. Basically, there are a lot of results that all achieve square root t or square root t log t for different versions of online stochastic bin packing. All of them, to be clear, sort of make different assumptions and arguably weaker assumptions than we do. We get this constant loss, but with the big caveat that it's problem dependent. And this is based on joint work with Sid. Yes, it would be dependent on the item probability arrival. It would be dependent on, if I'm perfectly honest, the biggest piece that it's dependent on is all of these results here. You tend to see something where the B, the bin size, is a well-behaved sort of constant, like the B shows up as just B. And Sid and I, in our result, don't have a nice bound on what this B, how it would show up. So this constant M might hide something that's exponential in B, but constant in T.
And this is for known distribution?
Also for unknown. Unknown as long as it's discrete and as long as each arrival type is not too rare. Yeah. In terms of modeling, as I mentioned before, I am quite a big fan of this idea of the heads up for the horizon end. I think it's a nice in-between sort of the adversarial, the stochastic, and the known setting. And one thing that's nice is that the positive results that we get are comparable to what one would get if we just knew the horizon a priori. And as I mentioned, I would view it in many applications as the most realistic. In terms of the length of exchangeable actions, the nice thing about this framework is that it allows us to capture a wide set of problems. Not all problems, of course. So in particular, as I mentioned, Wayna is going to be talking in a little bit about a set of problems where it would not hold. Generally, when there are arrivals and departures, as is often the case in inventory problems, that would not work. And our results, for the most part, are instance dependent, which is not like my preference, of course, but at least for some of the problems we consider, for example, overbooking, we can show that it's provably unavoidable. So to summarize, we can view these exchangeable action models as an algorithmic and analytical framework where we see how different sets of assumptions would give us constant regret. We get new guarantees for the bin packing problem and this overbooking problem. And while we don't have the minimum set of assumptions, we do get, in a sense, a minimal set assumptions. And I'll stop here and be happy to take any questions. Thank you.
So here you're getting a constant regret by making a stability assumption. Suppose you don't have stability, but as a function of growing instability, do you know how the regret will?
Yes. I think I'd have, to be honest, I'd have to look at the paper. I think it's either linear or quadratic. It's not like 2 to the delta.
I mean, it has to stop at square root t, I guess. For example, in your problem, that is a variance that is
because we are sort of treating it as a constant, we're not being super tight at every bound that we're taking. So it might be that it's linear in T just because the guarantee that we prove is not perfectly tight. But yes, you're right. There's only so much loss that you can imagine. And as I mentioned very earlier, like getting square root T is like if you knew the problem is super non-stable, as for example, this maximum of x1 and x2, yes, then you shouldn't be using our algorithm and you should just use what's optimal there, which will give you square root t loss.
Do you think that there's value in getting approximation ratio results in problems?
I would say no. And the reason is that you can think of the constant regret as a 1 minus O of 1 over t approximation ratio. So, I mean, there's always a space for everything. So if the assumptions that we're making clearly do not hold, then you may want to just use like something more robust that has a competitive ratio where you're more certain that you will get some guarantee. If you believe that the sort of assumptions that we hold either hold true or at least approximately hold true, then you may want to get this here. And again, like that's, yeah, I would say when these assumptions hold, then like this is about as good as you can hope.
Doesn't it depend on whether opt grows with t?
That
Like what if opt is very small?
would not usually be a problem. I mean, actually, I should be careful. If opt is a constant, then I guess you could achieve 0 and still be within a constant of opt. So yes, you're right. In that case, a 2 approximate, like the competitive ratio of 2 would be better. So yes, I agree. If opt is going to be really small, if opt is going to be constant, then you.
In that case, if you're just talking about additive versus multiplicative constant, I mean, these are still the same thing, right? It's not like competitive ratio is going to give you something much more insightful than something difference between two constants is going to give. So, right? So, and this t to the 3/4 time window that you asked for a heads up, like is that like minimum or like square root is okay? Or
if I was very, very careful about the analysis, I could get square root t log t with the appropriate constant. With t to the 1/2 plus epsilon, I don't need to be careful, but I need to carry an epsilon around. With t to the 3/4, I can be very comfortable. But yeah, that is really like that was for simplicity in the talk.
Maybe one more question and then we can break if anyone has.
Just make sure in the BIM packing it was necessary to have the p min, like a low bound on item arrivals, if
Yes.
a constant number of guys.
Yes, and that's not only for bin, that's across. Yeah.
I had to start the workshop one time. I had forgotten to properly introduce Daniel, who is a professor of operations management at MIT. He's a recipient of numerous awards, including the George Danzig Dissertation Award, the Daniel Wagner Prize for Excellence in War, multiple best ever awards, including the Informs Property Society's Best Ever Award, ACM Swigac's Award, and so many awards basically. And after his PhD at Cornell, he spent a year at the Lyft Marketplace app in New York City. Thanks, David.
Right, so let's get back after the break at 11 for Vina's talk. We'll continue talking about big questions.